Picture a man standing alone in the middle of a rail yard. It's 1923. The sun hasn't risen yet, but the roundhouse foreman is already at his post. In front of him sits a Baldwin 210-2 Santa Fe type locomotive. Fully loaded with water and coal, this machine weighs just over 500,000 pounds. That's 250 tons of iron, steel, brass, and fire. And this one man is about to spin it around like a toy on a Lazy Susan. No electric motor, no hydraulic system, no team of horses, just one worker, a long iron bar, and an understanding of physics that most engineers today would struggle to explain. If you've ever wondered how the railroads actually worked, not the romantic version with the golden spike and the champagne, but the daily reality of moving thousands of tons of steel through yards designed before anyone had reliable electricity, this is where it happened. On the turntable. The device itself looks deceptively simple. A bridge, roughly 100 feet long, sitting on a central pivot. Tracks run across the top. The locomotive rolls onto it, the bridge rotates, and the engine rolls off facing a new direction. Simple in concept. Absolutely brutal in execution. Because here's what the history books leave out. Those early turntables weren't powered by anything except human muscle. Men rotated locomotives weighing hundreds of tons using nothing but mechanical advantage, leverage, and a complete disregard for what we'd now call workplace safety. To understand why they built these things, you have to understand a fundamental limitation of steam locomotives. They couldn't reverse efficiently. Sure, every locomotive had a reverse gear. You could technically run one backwards, but the cab was designed for forward operation. The engineer's view to the rear was obstructed by the tender, that car carrying coal and water. Running in reverse meant running half-blind. For short distances in the yard, that was acceptable. For mainline operation over dozens or hundreds of miles, it was dangerous to the point of being suicidal. You couldn't see signals, you couldn't see obstacles on the track, you couldn't see another train coming until it was far too late. And even if visibility weren't an issue, the mechanical design favored forward operation. The driving wheels were positioned to provide maximum traction when pulling forward. Valve timing was optimized for forward running. The entire machine was built around the assumption it would travel in one direction. So every terminal, every major rail yard, every roundhouse needed a way to turn locomotives around. The turntable wasn't optional equipment, it was as essential as the tracks themselves. The earliest American turntables appeared in the 1830s, and they were laughably small by later standards. 15 feet across, 20 feet, just big enough for the tiny locomotives of that era. Were engines that weighed perhaps 10 tons fully loaded. The first railroads in America used engines imported from England, delicate machines with names like the Stourbridge Lion, and they required delicate handling. Those early turntables were little more than wooden platforms on central posts. A few men could push them around by hand without any mechanical assistance. The locomotives were small enough that brute force was sufficient, but locomotives grew and grew and kept growing. For by the Civil War, engines weighed 50 tons. The demands of war accelerated development. Armies needed to move men and supplies faster, in greater quantities, over longer distances. Locomotive builders responded with bigger, heavier, more powerful machines. By 1900, locomotives had crossed 100 tons. The 440 American type that had been standard in the 1860s gave way to larger 460 10-wheelers, then 462 Pacifics, then 282 Mikados. Each new wheel arrangement brought more weight, more power, and more challenges for the men who had to turn them around. The great articulated locomotives of the 1940s, machines like the Union Pacific Big Boy, tipped the scales at over 600 tons, including their tenders. These were the largest steam locomotives ever built anywhere in the world, and turning them around required engineering that pushed the limits of what seemed physically possible. Every time locomotives got bigger, someone had to figure out how to turn them around. And for most of American railroad history, that someone was a worker standing at the end of a long iron lever, pushing with everything he had. The physics of how this worked is genuinely elegant. Consider a seesaw. When it's balanced with equal weight on both sides of the pivot, it takes almost no effort to tip it one way or the other. The turntable used this same principle, but in a circular motion. The locomotive would roll onto the bridge until its center of gravity sat directly over the central pivot point. At that moment, the entire assembly was balanced. The weight pressing down on the pivot might be 500 tons, but the rotational force required to spin it was dramatically less. Think of it this way: if you tried to lift a 500-ton locomotive straight up, you'd need 500 tons of force. But if that weight is perfectly balanced on a pivot, you're not lifting anything. You're just overcoming friction and inertia to start the rotation. This is where the engineering genius came in. The pivot bearing at the center of the turntable had to be nearly frictionless. Early designs used a simple iron post sitting in an iron socket. The friction was enormous. Workers had to push much harder than physics said they should, because half their effort was being eaten by metal grinding against metal. Later, turntables employed roller bearings, sometimes dozens of them, arranged in a circle beneath the central pivot. As the bridge rotated, these rollers turned, converting sliding friction into rolling friction. The difference was dramatic. What had required 4 men might now require 1. Some used what were called king posts, with hardened steel contact points machined to tolerances that would impress modern machinists. These contact points were ground smooth, then polished, then fitted together with gaps measured in thousandths of an inch. But the work required craftsmen who understood metallurgy, geometry, and mechanical engineering at a level that simply didn't exist in formal education at the time. They learned on the job, through years of apprenticeship, through trial and error that sometimes ended in catastrophic failure. The outer edge of the turntable ran on wheels that rolled along a circular track called the rim rail. These wheels supported some of the weight and provided stability. But the real trick was keeping most of the load on that central bearing where friction could be minimized. Engineers debated endlessly about the optimal distribution. Too much weight on the rim wheels and you had a dozen friction points instead of 1. Too little and the bridge became unstable, wobbling as it rotated. Every railroad had its own philosophy, its own preferred designs, its own arguments about what worked best. The construction of a turntable pit was itself a major engineering project. Workers excavated a circular pit, sometimes 15 feet deep, lined with concrete or stone masonry. Drainage systems had to be installed because a flooded pit was useless. The center foundation for the pivot bearing had to be absolutely level and rock solid, capable of supporting hundreds of tons without settling or shifting. In areas with poor soil conditions, engineers drove wooden or steel pilings dozens of feet into the ground to create stable foundations. The cost could exceed the cost of the turntable bridge itself. Railroads argued constantly about whether to invest in proper pit construction or save money and deal with maintenance problems later. Water played a critical role that almost nobody talks about anymore. Many large turntables floated the central bearing in a bath of water mixed with graphite lubricant. The water served multiple purposes. It reduced friction dramatically. It carried away heat generated by the bearing under load, and it provided a self-leveling mechanism that kept the bridge from binding when temperatures changed and metal expanded or contracted. The water bath turntables were engineering marvels, but they created their own maintenance headaches. The water had to be kept at the right level. Too low and the bearing ran dry, friction spiked, and workers noticed immediately that something felt wrong. Too high and water sloshed onto the pit floor, creating slip hazards and accelerating rust on any exposed iron. In the coldest months, workers had to keep fires burning beneath the pit to prevent the water bath from freezing. If the water froze, the turntable locked solid. Locomotives couldn't be turned. Operations ground to a halt. Men worked through blizzards and ice storms, keeping those fires lit because there was no alternative. The fire tending was often assigned to the youngest workers, boys really, 15 or 16 years old. They'd spend entire shifts in below-zero temperatures, feeding coal into pit stoves, breaking up ice that tried to form around the bearing, breathing smoke and frozen air until their lungs burned. It was considered light duty, a good way to learn the railroad. Now comes the part that separates the theoretical from the brutal reality. Even with perfect balance and minimal friction, a 500-ton locomotive has tremendous inertia. Getting it moving from a dead stop required significant force, and stopping it before it overshot the target track required just as much. The primary method of rotation was the Armstrong method, named not for any inventor, but for the arms of the men who did the work. A long iron bar, sometimes 15 or 20 feet, extended from the edge of the turntable. The worker would grasp this bar and walk in a circle, pushing the entire assembly around. On a well-maintained turntable with proper lubrication, one man could start a balanced locomotive rotating. Getting it up to walking speed might take a minute or two, but it was physically possible. The trick was leverage. That long bar multiplied the worker's force. A man pushing with 50 pounds of force at the end of a 15-foot bar generated 750 foot-pounds of torque at the pivot. Not enough to lift the locomotive, but enough to overcome bearing friction and start the rotation. Once moving, the turntable wanted to keep moving. Newton's first law in action. The worker's job shifted from pushing to guiding, keeping the rotation smooth, adjusting speed to bring the bridge into alignment with the target track. The danger came at the other end. Stopping. You've started 500 tons rotating. Conservation of momentum doesn't care about your work schedule. That mass wants to keep moving. The worker had to lean back against the bar, using his entire body weight as a brake, gradually slowing the rotation until the bridge aligned with the exit track. This required judgment that couldn't be taught in a classroom. You had to feel how fast the bridge was turning, calculate mentally how much momentum remained, begin braking at exactly the right moment. Too early and you'd stop short, have to push the bridge the last few feet. Too late and you'd overshoot, have to reverse direction and try again. Experienced operators made it look easy. They'd walk the bridge around, so lean back, settle it into alignment with barely a tremor. New workers overshot constantly, or stopped short, or lost their grip and had to chase a spinning turntable across the pit. Misjudged the momentum and the bridge overshoots. Now you've got to push it back the other way. On a cold morning, when you're already exhausted from the previous 12 hours, when your hands are numb and your feet are slipping on icy decking, this felt like punishment from a cruel god. Broke jaws, shattered arms, trying to catch them in the face, broke jaws, shattered arms, trying to catch themselves as they fell. In 1911, a turntable operator in the Chicago and Northwestern yards at Proviso got his coat sleeve caught in the gearing mechanism. Before anyone could reach the emergency brake, the gears had pulled him in up to the shoulder. He survived, but never worked again. The arm was amputated at the shoulder joint. He was 34 years old with 3 children. In 1907, a Pennsylvania railroad hostler named Michael Donahue was walking the push bar on a freezing January night. The pit deck was slick with ice. His feet went out from under him. As he fell, his hand stayed on the bar, which was still moving with the momentum of a 200-ton locomotive. The bar dragged him across the deck before he could let go, dislocating his shoulder and fracturing his collarbone. He was back at work 3 weeks later because he couldn't afford not to be. These weren't isolated incidents. They were the background noise of railroad operations, expected, accepted, built into the cost of doing business. The railroads kept statistics on major accidents, derailments, and collisions that cost significant money to repair. They didn't keep statistics on turntable injuries. It wasn't worth the paperwork. For larger turntables, single-man operation wasn't practical. And the heaviest locomotives required crews of 2, 3, sometimes 4 men pushing together. They developed a rhythmic coordination, a working cadence that distributed effort efficiently. Call and response chants weren't just tradition. They kept everyone moving together so the load was shared. One man calling out the beat, the others responding, all pushing at the same moment. Fall out of rhythm and you carried more than your share. The man next to you carried less. Resentments built. In crews that worked together for years, developed bonds stronger than family because their lives depended on perfect coordination. The work followed strict hierarchies. The lead operator controlled the pace and called the commands. He decided when to push, when to brake, how to handle difficult loads. The other men followed. Challenging the lead operator's judgment was acceptable in the break room. On the turntable deck, his word was law. Some railroads installed what they called tractor drives on their turntables. These weren't tractors as we think of them. They were mechanical gear reduction systems, essentially a vertical capstan, connected through a series of gears to the turntable mechanism. The worker would walk in a tight circle, pushing a horizontal bar connected to the capstan, and the gearing would multiply his effort. A well-designed tractor drive could give a single worker the mechanical advantage of 5 or 6 men working together. The gear ratios were carefully calculated. First gear for starting heavy loads, second gear for cruising speed. The worker would shift between them based on how the turntable felt under his hands. But tractor drives added complexity. More gears meant more parts that could fail, more maintenance, more things to go wrong at the worst possible moment. Gears stripped, and chains broke, shafts sheared under peak loads. When a tractor drive failed mid-rotation, you had a partially turned locomotive stuck on a disabled turntable, blocking every other track in the roundhouse. Getting it moving again might take hours. Meanwhile, locomotives that needed to go into the roundhouse couldn't. Locomotives that needed to come out couldn't. The entire terminal backed up. The transition to powered turntables came gradually, and much later than you might expect. When electric turntables appeared in the early 1900s, but they were expensive to install and required reliable power supplies that many yards simply didn't have. Rural terminals might be miles from the nearest electrical generation. Even urban yards had unreliable power, with outages common and voltage fluctuations that could burn out motors. Air-powered turntables used compressed air from the railroad's existing infrastructure, since air brakes were already standard on trains, but they had their own problems. Air motors were finicky. They froze in winter when moisture in the airlines crystallized. Seals failed and had to be replaced constantly. Compressors broke down, and without compressed air, both the turntable and the train's brakes stopped working. The most reliable machine for decades remained the human being. Men showed up for work even when equipment didn't. They could adapt when things went wrong. They didn't require spare parts. So, manual turntables persisted well into the 1950s. There are credible reports of hand-operated turntables still in service through the 1960s on secondary lines, and short-line railroads that couldn't justify the capital expense of modernization. The big Class I railroads had converted to diesel and abandoned most of their turntables by then, but smaller operations kept the old ways alive out of necessity. The daily routine of a turntable operator was grueling in ways that modern workers would find almost unbelievable. Shifts ran 12 hours, sometimes longer during peak traffic periods. There was no overtime pay for most of the steam era. You worked until the work was done or until someone relieved you. If your relief didn't show up, you kept working. A busy roundhouse might turn 50 or 60 locomotives per shift. Each turn took 5 to 10 minutes depending on the size of the engine and the condition of the turntable. That's 7 or 8 hours of continuous physical labor, punctuated by brief waits while locomotives rolled on and off the bridge. There were no heated break rooms in the pit, no shelter from rain or snow or summer sun. You stood on that deck and you worked. You ate your lunch in 5-minute intervals when there was a gap in the traffic. You used whatever facilities were available, and which often meant walking to the roundhouse building, 100 feet or more from the turntable. Men developed their own ways of coping. Veterans taught newcomers which locomotives were well balanced and which ones always fought you, which engineers positioned their engines properly and which ones stopped short or long, throwing off the balance, which supervisors understood turntable work and which ones pushed for speed regardless of conditions. And the men who operated these machines developed skills that can't be documented in any manual. They could feel through the bar whether the locomotive was properly balanced, sense from the way the bridge moved, whether the bearings needed greasing. A slight hesitation in the rotation told them the center bearing was running dry. A grinding vibration meant the rim wheels were out of alignment. They knew their turntables like a musician knows an instrument. And the same turntable felt different in summer and winter, in wet weather and dry, under a light engine and under a maximum load. Every variable changed the calculation. Every shift required adaptation. And they paid for that knowledge with their bodies. Turntable operators developed distinctive physical ailments, chronic shoulder injuries from years of pushing against that iron bar. The rotator cuff was never meant for that kind of sustained lateral stress. Back problems from the constant rotational motion, the torque transmitted through the spine as they fought to control hundreds of tons of inertia. Arthritis in the hands from gripping cold metal in winter conditions, the joints swelling and stiffening until some men couldn't fully close their fists. Respiratory problems from breathing coal smoke and steam all day. Hearing loss from the constant noise of the roundhouse. Burns from steam escaping faulty locomotive fittings. Cuts from jagged metal edges that were never properly finished because smoothing them took time nobody was willing to spend. These weren't dramatic injuries that made headlines. They accumulated slowly, invisibly, until men in their 40s moved like men in their 70s. They weren't eligible for disability because nothing was officially wrong with them. They could still work, just more slowly, with more pain, until eventually they couldn't. The railroads kept few records of these occupational diseases. There was no workers' compensation for a worn-out shoulder. You worked until you couldn't, and then you found something else to do, or you didn't work at all. Some men moved to lighter duties, became car knockers inspecting freight cars or crossing guards at rural highway intersections. Others simply disappeared from the railroad's payroll, their subsequent lives unrecorded. The scale of the largest turntables still staggers the imagination. The Atchison, Topeka, and Santa Fe Railway's turntable at San Bernardino measured 130 feet across. Think about that distance. That's nearly half a football field. When a massive 484 Northern-type locomotive rolled onto that bridge, the operator standing at the far end was 65 feet from the engine's smoke box. The heat radiating from the boiler was still uncomfortably warm at that distance in summer. The Norfolk and Western Railway built turntables capable of handling their monstrous Y6 class articulated locomotives, engines that stretched over 100 feet including their tenders. These turntables had to be perfectly engineered because the consequences of failure were catastrophic. Imagine 500 tons dropping 3 feet into a pit because a bearing gave way. The impact would shatter the locomotive's frame. Flying metal would kill anyone standing nearby. The pit would be destroyed, and the roundhouse out of service for weeks or months. These weren't theoretical risks. They were calculated probabilities that engineers and accountants weighed against the cost of better materials and more frequent maintenance. In 1934, a turntable bearing failure at a major eastern yard dropped a locomotive and tender into the pit below. The engine's fireman was standing on the tender deck when it fell. He dropped 12 feet into a pit full of oily water, mechanical debris, and displaced track hardware. The recovery took 3 days. The railroad never officially disclosed whether he survived. His name was William Kearney. He was 28 years old. The roundhouse and turntable together formed the heart of steam railroad operations. The roundhouse itself was a semicircular or sometimes fully circular building with individual bays for locomotive maintenance. The turntable sat at the center, giving each bay direct access to the central rotation point. A locomotive would arrive from its run, take on water and coal at the service tracks, and then be turned on the turntable to face into its assigned bay. Mechanics would service it through the night, checking bearings, repacking piston rods, cleaning out flues, replacing worn components. The work happened around the clock because the railroad never stopped. The next morning, the turntable would swing around to that bay, the locomotive would roll forward onto the bridge, rotate to face the outbound tracks, and roll off ready for another day's work. This ballet of iron and fire repeated hundreds of times daily at major terminals. Chicago's rail yards, in their heyday, operated dozens of turntables simultaneously. The Illinois Central, the Chicago and Northwestern, the Burlington route, the Milwaukee Road, every major railroad had its Chicago terminal, and every terminal had its roundhouse and turntable. The night shift workers at these facilities lived in a world of coal smoke, escaping steam, the constant screech of metal on metal, and the ground-shaking rumble of engines rotating just feet away. The smell was distinctive, Coal smoke and hot oil, steam and sweat, the sulfurous stink of lubricated bearings, and the organic decay of leather drive belts. Men who worked roundhouses for years carried that smell in their clothes, their hair, their skin. Their wives complained, and their children were embarrassed to have fathers who came home reeking of the railroad. Accidents happened with numbing regularity. Some were mechanical failures, bearings seized, bridges jammed, track switches malfunctioned. These were bad enough. Others were human errors that the system punished without mercy. In 1918, a hostler at a Great Northern roundhouse in Montana failed to properly align the turntable with the exit track. The gap was perhaps 4 inches. In the darkness of early morning, without proper lighting, in a pit full of smoke and steam, it was invisible. The locomotive rolled forward off the bridge and dropped its front drivers into the pit. The boiler shifted, ruptured a steam line, and scalded the engineer so badly he died 3 days later. His name was Charles Mathers. He left a wife and 2 daughters. The hostler who had made the alignment error was 19 years old. He had been on the job for 6 weeks. He wasn't adequately trained because there was no formal training program. He wasn't properly supervised because his supervisor was responsible for 3 turntables simultaneously. He wasn't fired because replacements were hard to find. There was no investigation in any modern sense, no safety review, no procedure changes. The railroad noted the death in its monthly report, paid the engineer's widow a small settlement, and the 19-year-old went back to work the following night. He stayed with the railroad for another 30 years and never forgave himself. This was the arithmetic of American industry. Men were cheaper than machines. Training was faster than engineering out hazards. And the work had to get done. What makes this history harder to accept is understanding how little of it was necessary. Better lighting would have prevented that Montana accident. Cost perhaps $100. Clearer procedures would have prevented dozens of similar accidents. Cost nothing but the time to write them down. Proper supervision would have caught errors before they became fatalities. Would have required hiring more supervisors, perhaps, or reducing the scope of responsibility for existing ones. Mechanical interlocks that prevented movement when tracks weren't aligned existed. They were installed on some turntables, particularly those operated by electric motors. They weren't installed on manual turntables because nobody thought manual equipment was worth the expense. These solutions existed. They weren't implemented because they cost money, and workers' lives didn't appear on the balance sheet in any way that mattered to shareholders. The largest turntables ever built in North America were designed for the true monsters of American railroading. In the articulated locomotives that reached their peak during World War II were the largest steam engines ever constructed anywhere in the world. The Union Pacific Railroad's 4884 Big Boy class required turntables of at least 135 feet. These locomotives measured over 130 feet from the front of the engine to the back of the tender. They weighed 600 tons, fully loaded with coal and water. They could pull trains of 5,000 tons over mountain grades that defeated lesser engines. When one of these 600-ton engines rolled onto the turntable bridge, the structure flexed visibly under the load. Workers could feel the vibration through their boots as tons of steel settled onto the bearing. The deck plates shifted. The bridge groaned. Metal stressed in ways that testing couldn't fully anticipate. Operating a turntable under that kind of load wasn't routine work. It was controlled chaos. The margins for error were measured in inches, and a mistake could mean derailment, and damage to equipment worth more than most workers would earn in a lifetime, and potentially death. The railroads that operated these largest locomotives developed specialized crews for turntable duty. These weren't entry-level positions. Men worked their way up through years of progressively larger equipment before they were trusted with the biggest power. They started on branch line turntables, handling small switcher engines, graduated to intermediate duty with road freight locomotives. I finally earned the right to handle the articulated monsters that required every ounce of skill they developed. Even then, the work took its toll. In 1952, a big boy being turned at the Cheyenne Roundhouse got away from its operator. The locomotive's tender had been improperly loaded, with most of the coal weight toward the rear rather than evenly distributed. This shifted the center of gravity. Instead of balancing on the pivot, the entire assembly became front-heavy. When the operator released the brake to begin rotation, the bridge tilted. Not much, perhaps 3 degrees. But 3 degrees on a 135-foot bridge meant the front end dropped nearly 7 feet. The locomotive slid forward, its front end dropping toward the pit. 3 men scrambled clear. James Harrison, a 47-year-old father of 4 who had worked that roundhouse for 23 years, didn't move fast enough. The falling bridge caught him against the pit wall. The railroad recovered the locomotive. It went back into service after repairs. The dead man's name appeared in company records for exactly 1 pay period after his death, the time required to process his final wages. His widow received 6 months' salary as a settlement. She signed a release waiving all claims against the railroad. The transition away from steam locomotives made many turntables obsolete almost overnight. Diesel locomotives could operate equally well in both directions. They didn't have cabs designed for forward-only operation. The engineer had clear visibility in either direction. The mechanical design was symmetrical in ways that steam locomotives never were. The entire reason for turntables disappeared when the last steam engines were retired. Many railroads filled in their turntable pits, covered them over, built parking lots and maintenance facilities where roundhouses had stood, until the infrastructure that had been essential for a century became inconvenient within a decade. But not all turntables disappeared. Some survived because they served diesel facilities that still needed them for maintenance purposes. Certain repair operations were easier if the locomotive could be positioned in specific ways. A turntable was still useful, even if it wasn't strictly necessary. Others survived through neglect, abandoned but not destroyed. Waiting in overgrown yards for someone to remember they existed. In small towns across America, you can still find these ruins. The pit filled with rainwater and debris. The bridge rusted but recognizable. The rim rail visible beneath the weeds. The preservation movement that saved a handful of steam locomotives also saved some turntables. Railroad museums recognized that you couldn't tell the story of steam railroading without showing how locomotives were serviced, and that meant preserving roundhouses and their turntables. The Steamtown National Historic Site in Scranton, Pennsylvania, operates a fully functional turntable as part of their Living History program. Visitors can watch as a steam locomotive rolls onto the bridge and rotates to face the roundhouse bays. The operation uses a small electric motor now, but the fundamental mechanics remain unchanged from a century ago. The same central bearing, the same rim wheels, the same principle of balanced rotation. The Railroad Museum of Pennsylvania maintains historical turntable equipment. Volunteer docents explain to visitors how a single worker could rotate hundreds of tons, and most visitors walk away shaking their heads in disbelief. They try to imagine pushing that bar, feeling that weight, doing it shift after shift in the cold and dark. The B&O Railroad Museum in Baltimore houses one of the most significant collections of turntable history in the country. Their roundhouse dates to the 1884. The turntable has been restored to operating condition. On special event days, they demonstrate manual operation for visitors, giving a glimpse of what the work actually looked like. Perhaps most remarkably, a handful of turntables remain in active commercial service. Short-line railroads and industrial operations that can't justify building new facilities sometimes find themselves maintaining century-old turntables because replacement would cost millions. These relics of the steam era continue rotating modern locomotives, their original builders long forgotten, their original operators even further from memory. The Durbin and Greenbrier Valley Railroad in West Virginia operates heritage steam excursions using a turntable built before World War I. When the locomotive reaches the end of the line, it's turned manually, using the same Armstrong method that would have been familiar to workers in 1910. And tourists watch as railroad workers push against that long iron bar, walking in circles, and they take photographs and marvel at the spectacle. Few of them think about the generations of workers who did this not for spectacle but for survival, Who did it in blizzards and heat waves, in darkness and exhaustion, because trains had to run and someone had to turn them around. Standing at a turntable pit today, if you're lucky enough to find one that hasn't been filled in or paved over, you can sometimes see evidence of the men who worked there, footholds worn into stone coping from thousands of workers bracing themselves against the push bar. Grooves in the rim rail from decades of steel wheels rolling past. Bolt holes, where long-vanished equipment was mounted and remounted as technologies changed. Patches in the concrete where repairs were made after accidents. Scorch marks where fire pots burned through winter nights. These marks are the only monuments most turntable workers ever received. They weren't glamorous figures. They don't appear in the railroad histories that celebrate engineering achievements and business tycoons. The names of the men who built the Transcontinental Railroad are famous: Grenville Dodge, Thomas Durant, Collis Huntington, Leland Stanford. We name streets after them, put their faces on stamps. The names of the men who turned locomotives around day after day, year after year, like making those railroads actually function, are known only to their descendants if they're known at all. William Kearney, Charles Mathers, James Harrison, Michael Donahue, names I found in accident reports and pension records, not in history books. This is the nature of infrastructure work. The more essential it is, the more invisible it becomes. The more perfectly something functions, the less anyone thinks about it. Those turntables worked so well, were operated so reliably, that the railroads came to take them for granted, and the men who made them work were taken for granted along with them. There's a philosophical weight to this history that's difficult to escape. We are beneficiaries of labor that killed people. The goods that moved on those railroads, the economic growth those railroads enabled, the country that those railroads helped build, all of it was paid for partly in human lives. Not dramatically, and not in single catastrophic accidents that made headlines, but in the daily grinding down of bodies doing work that was too hard, too dangerous, too poorly compensated. The turntable operator who worked for 30 years and retired with a broken body wasn't a victim of any single incident. He was a victim of a system that treated his physical destruction as an acceptable operating cost. The railroad got 30 years of labor. He got arthritis and a pension that didn't cover his medical bills. Shouldn't we don't get to undo that history? The debt was paid in a currency that can't be refunded. What we can do is remember. Understand what was done and what it cost and who paid. Stand at the edge of an old turntable pit and think about the men who stood there before us, pushing against that iron bar in the darkness, and recognize that their labor is part of what we inherited. The next time you see a train passing, diesel now, almost certainly, think about the infrastructure that made railroads possible, not just the tracks and the bridges and the grand stations, but the turntables and roundhouses where locomotives were serviced and turned. Think about the men who did that work. They didn't build monuments, they built a nation, and they did it one rotation at a time. If you made it this far, you understand something about American history that most people never learn. The romantic version leaves out the turntables. It leaves out the Armstrong method and the frozen bearings, and the men who lost arms to gearing mechanisms. It leaves out William Kearney and Charles Mathers and James Harrison and Michael Donahue. The real version includes all of it: the engineering genius and the human cost, the elegant physics and the brutal labor, the machines that seemed impossible and the workers who made them possible anyway. That's the history worth knowing. The history that doesn't pretend we got here without paying for it. Subscribe if you want more stories like this. Real history, no sanitizing, no looking away from what actually happened and what it actually cost. There's a video on screen right now about another piece of forgotten infrastructure that built this country. Click it. The work continues.